Kia ora tātou. Hope you're all doing really well. You may be watching this video quite a long time after I've recorded it, but it's worth noting for the historical record that recording this one at home in the middle of the COVID-19 lockdown, so yeah, it's a strange world that we're finding ourselves in right now, but it's still a good time to learn some mathematics. Okay, so we're going to return to the idea of transformations as we were studying a bit earlier. So remember the general idea of a transformation. A transformation takes something in, which for us will be a vector x, and then it does something to it to produce some kind of output, which t of x. So we met matrix transformations when we figured out matrix multiplication, and for us then we used t of x was the matrix A times x. Okay, now wouldn't it be cool if we could transform an expression like x is a linear combination of some other vectors by transforming all the pieces individually? For example, if t of x was actually just equivalent to a1 t of x1 plus a2 t of x2 through to ak t of xk, that could potentially make life a whole lot easier for us, because if those xi's were basis vectors, for example, we'd only need to know how to do our transformation on just those vectors, and then any other vector could just be built out of linear combinations of those transformed ones. So transformations that have this property, we say obey a superposition principle. And these transformations are called linear transformations. Now this idea is actually huge, and it's fundamental to, for example, creating models of things that change over time, which we call dynamical systems, signal processing, such as in communications and music, and many, many others. So if you continue to study more maths, science, or engineering, you'll likely meet this principle again many, many times over. All right, we need a bit of terminology to formalize this stuff a bit. So firstly, we need to indicate the set that our vectors are coming from, which is called the domain, and the set where our results live, which we call the codomain. And we typically use the notation T colon Rn to Rm. We read that as the transformation T that takes in a vector in Rn and produces one in Rm. So here, Rn is the domain and Rm is the codomain. Now when we map an individual vector x, we call t of x the image of x under t. And when we collect the images of everything in the domain together, the resulting set of all possible outputs is called the range of the transformation, which we can indicate in set notation as the set of all t of x's where x comes from our domain. Now the range is not necessarily the whole of the codomain, but it is definitely contained inside of it. Now we have what we need to define a linear transformation properly. So a transformation T that maps Rn onto Rm is linear if T of u plus v is equal to T of u plus T of v for all vectors u, v, and Rn, and also T of c times u is equal to c times T of u for all vectors u and Rn and scalars c. Now we can wrap those two up into an equivalent expression, which just says that T of cu plus dv is equal to c times T of u plus d times T of v, where the c and d are scalars. So this property is the other two kind of in one, and it's what we often just use to check that a transformation is linear. One final piece of useful information, T of 0 always gives us the 0 vector. You can use the scalar multiplication one to figure that one out. Okay, so we need an example to start wrapping our heads around how this works. So we'll start with quite a simple one. So the transformation from R2 to R2, defined by T of x is equal to a scalar r times x, is called a contraction when r is between 0 and 1, and a dilation when r is greater than 1. So let's use our definition to show that this is a linear transformation. So we'll use the second property. So we're going to take T of cu plus dv. Now for us that means r times cu plus dv. We can just rearrange and expand a little bit, which will give us c times ru plus d times rv. Now ru is just t of u and rv is just t of v, so that equals c times t of u plus c times t of v. So that's what we had to show that it was linear. So our scaling transformation is definitely a linear transformation. Okay, so now let's go back to those matrix transformations we were looking at earlier on. So this will be a transformation T from Rn to Rm, defined by T of x is equal to A times x. Now A will have to be an M by N matrix for that to make sense. So just as an aside, we sometimes define our transformations in a slightly shorter way. If we didn't want to give it a name T, we could just write the transformation where x is mapped to, and there's a little bar on the arrow this time, A times x. But here we'll stick with having a name because it's useful, and we'll show it's linear the same way as before. So let u and v be vectors in Rn and c and d be scalars. Then again, we'll start on the left-hand side with that same property. T of c times u plus d times v is, for us, this time we're multiplying by a. So that will be a times cu plus dv. Again, this is very similar to our previous one. We'll expand and rearrange slightly, so it'll be c times au plus d times av. I've tried to get those two pieces separate because what I want to get to is replacing those au and av terms with t of u and t of v. So that will equal c times t of u plus d times t of v. Cool, so that means any matrix transformation is therefore linear. So let's look at a concrete example now of a matrix transformation to try and wrap our head around some of these concepts a bit better. So something we might often want to do is find whether a given vector is in the range of a matrix transformation. So we'll take a matrix A to be 1, 0, 1, 1, negative 2, 3, and two vectors C is 1, 2, 1, and B is 0, 1, 2. Okay, so our transformation is going to take in a vector in R2, and it's going to produce a vector in R3, and it will be defined by T of x is equal to A times x. So the question we want to answer is, are the vectors C and B in the range of our transformation T? We'll do C first. So what we wanted to know is there a vector x in R2, that's the domain of T, such that T of x is equal to C, i.e. A times x is equal to C. So now actually we're back in our familiar realm of solving linear equations. So we can just solve this by building the augmented matrix with A and C and trying to solve it. So maybe if you want a bit of extra practice with this, you might want to pause your video and try and work this one through yourself before continuing. But what we get is that our augmented matrix will be 1, 0, 1, 1, 1, 2, negative 2, 3, 1. Clearing out the first column, that will give us the matrix 1, 0, 1, 0, 1, 1, and 0, 3, 3. And then finally, we just take off 3 of row 2 from row 3, and that will give us the row echelon form 1, 0, 1, 0, 1, 1, and 0, 0, 0. Okay, we can stop at this point. Remember, it's an augmented matrix. So what this is telling us is that x1 is equal to 1, and x2 is also equal to 1. So there is a solution here, and in this particular case, it happens to be a unique one. And so it is indeed true that C is in the range of T, because A times the vector 1, 1 will give us C. Now let's try and do the same thing again for B. Once again, we'll build the augmented matrix and row reduce it. So I'm going to take it to row echelon form, which will give me the matrix 1, 0, 0, 0, 1, 1, and this time the bottom row is 0, 0, negative 1. That bottom row tells us that our system is inconsistent, meaning there are no solutions, and therefore B is not in the range of T, but it is in the codomain. Okay, so the codomain and the range are slightly different things. The range is the actual possible outputs. The codomain is where they live, so the range is inside of that. Okay, so that's cool. So now we've established that whenever we have a matrix transformation, it's linear, but we can actually say something more powerful than that, because actually all linear transformations from Rn to Rm actually have to be matrix transformations. Okay, so that's quite a big statement. So why is this? Well, what we're going to do is we're going to take an arbitrary vector x, and we're going to put it through an arbitrary linear transformation and show that we can represent this using a matrix. So remember that we can express our vector x in terms of our standard basis e1 through to en as x is equal to x1 e1 plus x2 e2 through to plus xn en. So what that means is if I were to transform it, t of x, because that transformation is linear, will be x1 t of e1 plus x2 t of e2 through to xn t of en. Okay, let's just think about what we've got here. So t of e1, that's a vector in Rm, so is t of e2. So what I've actually put down here is a linear combination of vectors in Rm. And we know that linear combinations can be written as matrix vector products. So that means that t of x will actually be the matrix with all those Rm vectors as columns. So it'll be the matrix t of e1, t of e2, all the way through to t of en, times the vector x1, x2 through to xn. But actually, look, we've just turned it into a matrix transformation. That matrix with all the t's of the basis vectors as columns, that's our matrix of the transformation. So we could write this down as A times X. So the matrix A is called the standard matrix of the linear transformation. So let's just finish by figuring out what that matrix is for the scaling transformation we did just before. So again, just to recap, we got that transformation T from R2 to R2 given by T of X as a scalar R times X. Then let's build our matrix. So the matrix A is therefore given by the matrix with T of E1 as the first column and T of E2 as the second column. So T of E1, that's just R times E1, and T of E2, that's just R times E2. So that gives us R0 and then 0R, which is just actually R times the identity. So that means our matrix of the transformation is R times I, and T of X can therefore be written as T of X equals A times X, where the matrix A is Ri. Now maybe this is quite obvious if you think about it in retrospect. So what we'll do next time is we'll show that many interesting geometrical transformations can actually be built as linear transformations, or they are linear transformations, and we'll spend some time playing with these and finding their standard matrices. But for now though, that's enough. Keep safe, and we'll see you in the next video. Ka kite anō.